right, good morning, everyone. Welcome to the first oral session for the final day of CoRL, and good to see we still have good numbers in the audience. My name is Michael Milford. I'm one of the directors of the QUT Centre for Robotics. I'm one of your chairs for this session, and my co-chair is Nils Wild from TU Delft, and we're very happy to be bringing you a range of talks this morning. So for this session, we have 5 papers along the themes of autonomous vehicles and navigation. We are being encouraged to encourage questions. And so I'll talk a little bit about what these papers are going to cover thematically, so you can start thinking of the good questions or the hard questions now instead of when the paper is just being presented. So we'll start with some work on reinforcement learning, leveraging prior information for robust long-range navigation. We'll move into the problem of what you do when your autonomous vehicle scans are occluded or missing chunks and what you can do to solve those missing bits. We'll talk about how you can more efficiently optimize what you train your data on. So identifying the difficult scenarios that you should bias your training data sets to represent. We'll talk about bridging the old divide between image-based navigation and object-based navigation. And finally, we'll talk about defending autonomous vehicles against attack. So what do you do when one of the vehicles in the environment is deceptively tweaking its trajectory slightly in order to make your autonomous vehicle do the wrong thing and crash? So you can see there's really 2 themes across all of this work. The themes of, which has resonated throughout the conference, the theme of how you can do more with less, I guess would be the one theme. And the second theme is how you can make your system, your autonomous vehicle system or your navigation system robust to both accidental attack because the environment is challenging, and intentional attack when something in the environment is trying to screw with you. Now, we want lots of questions. We were forced to attend too many industry parties last night, and so we don't want to have to ask too many questions as chairs. And to incentivize it very tokenistically, anyone who asks a question will get a free book on autonomous vehicles, which is pitched at 12-year-olds, professors, and CEOs of autonomous vehicle companies. So start thinking about your questions now, and we can have a great session. So our first speaker, I'm happy to introduce, is Dhruv Shah.
All right. Okay, hello everyone, and thank you for being here and not flying back before the conference is actually over. I'm Dhruv, and I'll be presenting our work on offline RL for visual navigation. This work was jointly led by my undergrad Arjun, who is applying for PhD programs, so look out for his application. Okay, of the many ways I think mobile robots can change our lives, impact our lives, one that really appeals to me is having these cute little sidewalk delivery robots delivering you food and groceries from nearby stores. And as you can probably tell, it's doing a really good job of navigating between humans, negotiating traffic and so forth. So I guess navigation is solved and I can go back to my seat. Well, the catch here, much like the PR1 demo, is that all of these robots were kind of controlled remotely from distant countries. And it's not autonomous yet. There are autonomous ways to do it. Some 2 years ago, we tried kind of a learning-based navigation system that could do something similar. And while it does a fairly decent job of, it's a gimmick, but it goes to destinations and delivers packages, it's not really mindful of semantics like crossing the grassy lanes and, not sticking to the pavement and so forth. So in this paper, what we'll do is we'll talk about how we can train real-world control policies that respect constraints like stay in your lane or stay on the pavement and don't veer off into the grass. And I should acknowledge, like I said before, that there's been several successful attempts, whole companies based on this, that involve variants of 3D understanding, machine learning, and so forth. But I'll specifically focus on the challenges with training control policies that can have customizable behaviors that the user can specify. Just so we're on the same page, our setting is that of visual navigation, where a robot with an egocentric RGB camera, it's no depth, just RGB camera, is dropped in a previously seen environment. to seek a goal that is denoted by a GPS location. And I should emphasize again that the robot has no depth and no 3D maps. And when I say seen here, what I really mean is it has visual trajectories from a pre-exploration. Solving this task requires more than just a policy that can reach a goal, as we just saw earlier. So for instance, if this was a general purpose navigation system that is in New Zealand, it would see a lot of boards that look like this. And there's a lot of boards that look like this. So maybe it needs to know that it should drive on the left side of the road, or if it's kind of a sidewalk robot, it should stick to its sidewalk and not veer off into someone's driveway or onto the road, or maybe just avoid this kind lady's lawn because she's not happy about it. In each of these cases, we need a way not only to specify the task and constraints, but also a way to kind of optimize these constraints on top of being able to reach the goal. As you would guess, an effective way of doing so is using reinforcement learning to specify these constraints in the form of a reward function, and then optimize them with your favorite RL algorithm. Unfortunately, as again, many of us know that, collecting real-world rollouts with online RL is really, really expensive, often of the order of several lifetimes of a robot, leave alone a human. And even if you do get this to work, flat or end-to-end policies that are trained with reinforcement learning are not really good at doing long horizon tasks. And difficulties with value propagation, difficulties with credit assignment. So really, we need to do something about it. We kind of think about a simple way to eliminate online rollouts is just training your policies with this new thing called offline RL, which is just RL, different variants of an RL algorithm that are trained on an offline data set of experience. And to deal with issues like value propagation over long horizons, we use a topological graph in conjunction with kind of the goal condition value functions that we talked about. So what do I mean when I say a topological graph? Yes, such a graph has two main components. It is a distance function and a learned control policy. Given sample trajectories from the target environment, the learned distance function infers some sort of connectivity between these observations, which gives you the topological layout of the environment. On top of this, you can have your favorite graph search algorithm that picks out a sequence of sub-goal nodes that get you to your desired goal. And you feed this sequence of sub-goals to your control policy, which is, again, this could be trained with RL. And one sub-goal at a time, the robot kind of plans its way to the goal. And it's fairly easy to see that the control policy can be trained with RL. That's what everyone's doing. But how do we get this distance function, which we need for inferring the connectivity in the graph? So to kind of combine this notion of reinforcement learning with topological graphs, we use an important observation that the value function trained with any Q-learning algorithm can be interpreted as a distance function in a lot of cases. So as an example, for the simplest case where the reward is just a -1 survival penalty, shouldn't call it a reward, and no discounting, it's very easy to see because the optimal values for that reward function is actually the negative temporal distance. So if you train an RL policy with the specific reward function, it is exactly the same as doing distance estimation. But more importantly, this equivalence between values and distances kind of lets you do more creative things. So if I told you had a solar robot, you could design a reward function where you discount kind of desirable transitions like driving in the sun. And what this would implicitly do is encourage the policy to maybe avoid shaded areas and maybe take a detour, even if it means it's going to spend a little bit more time in the sun. And that's kind of what our system is. We're calling this Rewind, which stands for reinforcement learning for visual navigation from prior data. Schematically, our system uses different types of reward functions like staying on the sidewalks, driving in the sun, driving on the grass, and so forth. And you train different Q functions for each of these reward functions. But when you do Q learning, this gives you two things for free, which is the value function or the distance function that we talked about, and a control policy, which you can use in conjunction with the topological graph for high-level planning as well as low-level control. In fact, under certain assumptions that I won't get to here, it can be shown that finding the minimum cost path in this value graph is actually equivalent to recovering the optimal policy pi star for this reward function. So we'll quickly look at some experiments. So we have three policies here, one corresponding to going straight, one corresponding to driving on the grass, one corresponding to driving in the sun. And given the same kind of start and goal, we kind of find that these policies discover different paths in the environments. And quantitatively, you can kind of see that the first one finds the shortest path, whereas the others kind of optimize their respective utilities that you want to care about. Looking at kind of these policies in a different environment, from a third person view, the minimum distance policy, which is just not not giving any special reward is at the top right. The bottom left is a policy that's incentivized to walk on grass, and the bottom right is the one that's incentivized to walk on the pavement. And just by simple reward labeling, we can get policies that get to the goal in different ways just to meet user preferences. I'm going to skip some of the stuff that I had here and kind of quickly get to talking about what I meant earlier in terms of why flat policies are not sufficient. Most policies train end-to-end with RL, end up wanting to go in a straight line. They don't really optimize over long horizons. Whereas if you try to add a graph in the loop, on the left is our policy that uses RL. On the right is the policy that doesn't use RL. We find that the one that uses RL kind of actually cares about the reward function, whereas something trained with BC does not. Very quickly, we'll talk about limitations and dirty laundry, which apparently is spelled like fat. So I mentioned at the very start that we're working in a scene environment, and that can be a very restrictive setting for if you want to do exploration in new environments. This assumption can be lifted by incentivizing goal-directed exploration. It's something we studied in a recent RSS paper, and there's a very nice paper from Nuri Kim in this session, maybe 2 speakers after me. So please stick around for that if you're interested in that setting. And while we can train all of our policies in previously collected kind of, it is offline data, offline learning. It's not really kind of truly offline because the data was collected on that same robotic platform. And really a perfect idea offline learning system should leverage experience and mistakes of other robots. So we kind of studied a version of this in a follow-up paper, which I'm happy to discuss at the poster session. So yeah, that's my time. And please find me at the poster session across the lobby. It's not the one downstairs. Thank you.
Questions? There's one up in the back right. Get on your microphone.
Like, would I need like a equal amount of data for each path for this to choose among the paths, or if one path was underrepresented, somehow the offline learning would maybe like underestimate that? Thank you.
Great question. I think I should clarify that there's 2 versions of prior data in this setting. One is the offline data that the policy is trained on, and the other is data in the environment on which the planning happens. So I think the phenomena that you mentioned is kind of the second part, which is you need to have a fairly dense graph of the environment so that you can actually have multiple ways to get to the goal. And on that front, if you don't have multiple paths in your pre-exploration phase, it's not going to find multiple paths. The first one, which is kind of how you actually get policies from offline data, I would not say that has strong assumptions. We've tried training it from autonomous driving data. We've tried training it from Roombas navigating in different environments. So it's fairly easy to get the policy learning working.
So the policies you presented the examples were sun seeking,
Yeah.
following graphs. What sort of level of complexity of policy and policy combinations could you implement?
So I think, okay, so this is a great question. I should have included in my dirty laundry, which is that there's a very strict assumption here, which is the behavior that you expect to see eventually should be able, you should be able to express it in your reward function. And the kind of behaviors that you can express are behaviors that happen at the level of choosing subtasks, rather than behaviors like, oh, I want you to go really, really fast and drift like the auto rally stuff. If you want to do things like that, you might have to do things that don't really work with this framework.
All righty. So any other questions? Drew will be
at the poster.
Session.
Thank you.
So we've introduced the concept of autonomous, I guess you'd call off-road or semi-off-road vehicles. Those vehicles have sensors on them. Those sensors are often occluded because people and vehicles and other things get in the way. So our next speaker is going to talk about one potential solution to that. So welcome Yutao Han to the stage.
So my eyes are a little sensitive to brightness, so there's a lot of shiny lights up there. If any of you have been down here, you'll know, so thank you. All right, so How's it going, everybody? I'm going to talk about our work titled Planning Paths Through Occlusions in Urban Environments. And this is a collaboration between Oppo and Cornell. So if you don't know Oppo, you probably have heard of OnePlus. That's the company. So one of the issues with planning in general is how to handle occluded environments. So that's true for indoor and outdoor. Specifically, we wanted to focus on outdoor environments. So in this picture taken from the Kitty data set, you can see that there are some occluded spaces where they're hidden behind buildings or fences and trees, and we don't know what occupies those spaces. So you can imagine that this can affect the distance that we can planning, and also how informed we can plan the paths. Here's some previous work that I did. So in this paper, what you're seeing there is a semantically labeled point cloud that is being transformed to a bird's eye view. So you're taking a Google map view of the semantic LiDAR point cloud. So in this work, it required a manual annotation of the occluded spaces that you want to predict the labels for. And so what you're seeing in the second image is the sparse LiDAR point cloud. The white pixels are the pixels that you're trying to fill in. And then in the third image is the predicted semantic labels for those occluded spaces. And then we plan a path in the last image. There's also been some other work done in predictive modeling of unknown spaces targeted for indoor environments. Some of the recent advances in generative adversarial networks have been very useful for imaging painting. So similar to this previous task where we have unknown pixels we want to fill in. Also for domain transfer, specifically pix-to-pix, where you can take labels with semantic annotations and generate a realistic image. So what do we do? The first thing we did is we have a framework for using a predictive in-painting model for filling in occluded spaces, specifically for outdoor environments to allow for more informed path planning. We present a training loss that's tailored to the in-painting task. And we also provide a data set that is tailored for predictive modeling of occluded outdoor environments and planning in them. The basic pipeline of our work is that first we have an automatic network that is going to fill in the occluded spaces of a bird's eye view LiDAR scan. So in the first image, there's a bird's eye view of a sparse LiDAR scan. In the second image, we have an automatic predictive model which fills in the unknown pixels or the black pixels in this case. Third image, we detect some waypoints for path planning. In the fourth image, we can use any generic off-the-shelf planner to plan our paths. So for the model itself, we start with a baseline paired image algorithm, pix-to-pix, where they have a L1 loss between the generated image and the output image. One of the issues with that we notice is you can see that in the image all the way on the left, in that highlighted red circle, there are some sparse features in the initial LiDAR scan that are lost in the image all the way on the right, which is generated using just the pix-to-pix image, the pix-to-pix network. And so we also introduce an autoencoder self-preservation loss between the input source image, the LiDAR scan, and the generated image. And in our image, it's able to fill in the pixels surrounding the sparse features. Finally, we also use a ranking-based loss, which is going to encourage patches of generated and source images that are close to each other to have similar content. And our final training objective is going to be a combination of the GAN loss, the autoencoder self-preservation loss, and also the ranking-based loss. So for our model, we start with the in-painting model. We skeletonize the road using John's method to define the waypoints. And finally, we used a hybrid A-star planner. So just a use case here, you can see in the top row, the first image is an initial LiDAR scan. The second image is a ground truth. The orange oval highlights a region of the road that is occluded by a corner of a street. And so we'd like to figure out what's going on there. So our predictive model in the third image is able to partially fill in that region. The middle row might be kind of hard to see, but those are the skeletonized road pixels. And that we use for defining the waypoints. And then finally, in the last image, it shows our planner, our A-star planner. So you can see that by using the initial LiDAR planner, it's unable to plan and also account for the turn that's occluded by the street corner. Whereas by using our predictive model, you are able to account for that from a farther distance away. So our data set is derived from the Kitty 360 data set, which is an upgraded version of the Kitty data set. Basically, we transform the point clouds to a bird's eye view, and then we render pairs of bird's eye view frames that include the initial LiDAR scan and also the aggregated ground truth semantic maps. Some of the experiments we did include evaluating the road branch prediction. And so what that means is regions of the road where there's distinct behavior, such as at a fork in the road or at an intersection. We also evaluate for how far ahead we're able to plan ahead for occluded turns. And specifically, we noticed that for more difficult environments, which we define as environments that have more occluding obstacles, such as buildings or fences, the predictive algorithm becomes more and more significant. So here's a video. I figure out how to play this thing. That didn't work. How do I play the video? And can you play it? All right, so if you'll just use your imagination here for a minute. Basically, what this video shows is if you use the initial LiDAR, just a sparse LiDAR scan, it's unable to account for the turn coming up further ahead. Whereas if you use a predictive model, it's able to account for the turn from a longer distance and plan a path according to the occluded turn. And also, I should have said this earlier in the beginning, but in the problem statement of our work, we assume that it's an unmapped environment. So we don't have like an HD map or anything. Okay, some of the main takeaways, our framework allows for predictive modeling of occluded spaces. And also we notice that as the scene complexity increases with more obstacles, the predictive modeling becomes more important. Some of the dirty laundry. So we assume that we have localization of the vehicle. So the pose is a given. We also assume that semantic segmentations of the 3D point clouds are done in real time. And finally, we assume the train and test data is in the same domain. So you wouldn't want to train in one city and then try to deploy it in another city. So that wraps it up for my presentation.
All right, we have some questions. We'll go to the left first, please. Do you have a microphone on the left? Or you can just shout if you're comfortable.
Do you have any notion of uncertainty of your altitude? Perhaps your planner not perfectly trust your predictions, trust with more the data?
Right, that's actually a great point. So in this work, no, but we actually did consider that. So if you're familiar with the Bayesian neural networks, the work done by Yaron Gull, so we try to plan that to the network where we randomly drop out forward passes through our network. So the uncertainties didn't look too good from what we were working on, but that is something that we are considering, and that would be useful.
Hi, thank you for your interesting talk. So you already mentioned in your list, you that the domain gap between different cities is rather high. So did you do any experiments quantifying the size of the domain gap? Because I would also assume that evaluating on a different city with different topological structures would lead to inferior performance.
Right, that's a good point. We just evaluated using the Kitty data set, but yeah, that would be a good experiment to do.
All right, thank you for those questions. Oh, no, thank you for those questions. Let's thank Carla one more time. Yeah. All right, so we've encountered a difficult situation in terms of occlusion. We know that not all driving and planning tasks in an autonomous vehicle domain are equally hard. I know I struggled to reverse a car as part of my driving test. And so I had to concentrate on that particular subset of the data. And that links into the theme of our third talk for the day, which is really on how you can focus on evaluating difficulty and using that metric for difficulty to identify where you should prioritize your training data. So Ellie, please welcome Ellie Bronstein to the stage.
I think it's doing it or not. All right, 1 second.
I'm not a man.
I think I'll just try mirroring here. Okay. Yeah, okay, that's great. Thanks so much. All right. Okay, so yeah, hi everybody. I'm Ellie from Waymo Research, and today I'll be talking about this paper, embedding some. Oh, thank you. And today I'll be talking about embedding synthetic off-policy experience for autonomous driving via zero-shot curricula. So Waymo's goal is to build the world's most experienced driver, both for moving people and goods. So one way to approach this task is using classical optimization-based motion planning. However, this often involves bespoke components specific to the AV hardware or the deployment region and can require copious hand tuning in order to adapt to novel environments. So this, an alternative approach would be to use the vast amounts of experience collected by AV fleets and train ML-based planning agents in order to, which can exhibit complex behaviors and rapidly and automatically adapt to new areas. So reinforcement learning has been used in to create such agents in settings where the reward function is straightforward to define. However, due to the complex nature of driving, it's often difficult to specify a reward function to produce behavior that fully aligns with human expectations. So for this reason, we use imitation learning to learn a policy directly from expert demonstrations. Now, in many robotics and AV applications, the imitation learning based approaches commonly just treat all available training data equally. However, this can often produce agents that are not sufficiently robust to challenging and safety critical scenarios, an issue that cannot necessarily be addressed by simply collecting more training data. So to demonstrate this, we trained an imitative route condition planning agent on our entire training data set and just a random 10% sample of it. And we evaluated both by computing the failure rate, which is the rate at which the agent deviated from the route, collided with another road user, or drove off the road. And we found that the agent trained on just the 10% sample performed just as well as the agent trained on the entire data set, suggesting that simply adding more training data doesn't necessarily improve performance. Now, why is that the case? So this is because the vast majority of driving situations are really easy. Now, in about 3/4 of our data, there are no other moving road users, or they're too far away to necessarily interact with the AV. Less than 1/4 of scenarios are truly interactive, and only a really small fraction could be considered challenging. So to address this, we propose upsampling challenging and interactive scenarios during training, because these contain the most useful information. Now, it's difficult to identify the actual difficulty of a situation a priori in a way that generalizes across different environments and policies. So in this work, we propose a learned difficulty model that is able to identify and then upsample challenging scenarios to produce more robust planning agents. So we start with a large amount of data collected by our fleet of AVs in a variety of, using a variety of vehicle platforms in multiple deployment regions and planning policies. So we then shard this data into run segments or short snippets of recorded driving data. For each one of these segments, we generate one image, which contains the AV trajectory, and another image that contains the trajectories of other road users and of the road graph. And then we contrastively train a classifier to predict whether these two images, whether two images come from the same run segment. And this process allows us to generate a similarity-based run segment embedding. Now, to collect training data for a difficulty model, we leverage counterfactual data-driven simulation. During the course of regular AV development and testing, development planners are evaluated in simulation by having them control the data collecting vehicle and then computing key metrics such as collisions. So simulated collisions and near misses are then sent for human triage, in which labelers identify them as realistic or not. Now, using these difficulty labels and the run segment embeddings, we train a difficulty model to predict whether a run segment would result in a collision or a near miss upon simulation. Now, a key contribution of this work is this difficulty model and the way in which it is trained. Since we use data from a variety of vehicle platforms, different deployment regions, the difficulty model can be seen as marginalizing over a diverse distribution of development planners. This makes it more likely to be able to actually identify the inherent difficulty of a run segment and also zero-shot transfer to a substantially different planning agent. We use this model to then identify or predict the difficulty score for our entire data set. And here we show the score distribution, which, as expected, is characterized with this long tail of challenging scenarios. To allow for efficient and scalable upsampling, we partition the data set into 10 buckets, each corresponding to a decile of the data according to the difficulty scores. And here we show these different partitions using the shaded backgrounds in the plot. So up and down sampling can then be achieved by assigning sampling probabilities over these 10 buckets. So here's an example of the easiest bucket where there's just a straight, mostly empty road, and the planning agent basically just needs to learn to drive straight. This example is from a medium difficulty bucket where the planning agent needs to learn how to interact with some other slow-moving vehicles and handle intersections and traffic lights. And this is an example from the most challenging bucket that contains more difficult scenarios, such as this one, where the AV is driving very close to an articulated bus. And the planning agent needs to learn how to handle such extremely close interactions with care and without collisions. Now, we then designed several difficulty-based sampling strategies for training the planning agent. Now, the baseline variant simply uses the unbiased data distribution, while the highest variant trains on only the hardest bucket. The uniform variant approximates a uniform difficulty distribution by setting the weight of each bucket proportional to the range of scores in that bucket. And finally, the geometric variant implements a progression starting from equal weights per bucket and then up until to each bucket being weighted proportionally to the average score of that bucket. The effect of which is that it also upsamples challenging scenarios. Now, we found that each of our upsampling variants resulted in significantly lower collision rates and also comparable and off-road and route failure rates to the baseline, resulting in the lowest overall failure rates. Now, this key result demonstrates that run segments with the highest and high predicted difficulty scores actually contain the most useful information for good aggregate performance. So just an example, here is a narrow road with an oncoming car, and this is from the easiest segment. And you see the baseline agent collides with the oncoming car because it hasn't really trained on enough challenging scenarios. But in contrast, the geometric variant, which has upsampled such scenarios, is able to carefully nudge around the car and then proceed safely through the segment. However, we noticed that aggressive and extreme upsampling of difficult segments results in poor performance on the other end of the spectrum. And this is because the easier segments become too rare in the training data. So here we show performance on the easy, medium, and hard buckets. So the highest and uniform variants, as expected, perform the best on the hard bucket because they upsampled these segments the most. However, they perform quite poorly on the easy and medium buckets, worse than the baseline. Now, the geometric variant is able to address this issue by maintaining a broad coverage over the difficulty distribution at the beginning, and then progressively increasing the amount of challenging scenarios throughout training, yielding the lowest overall failure rates. Now, one of the limitations of our work is that the difficulty model was just predicting collisions and near misses, but there are other labels that would be helpful for a more comprehensive notion of difficulty. And similarly, there are additional evaluation metrics that we could consider, such as traffic law violations. And finally, while we tested this out with planning agents that were trained with model-based Gale and behavior cloning, that we could extend this to other learning algorithms in the future. So to summarize, we learned a difficulty model using counterfactual simulations from multiple development planners and deployment regions. And then we used this model to upsample challenging scenarios during training, which resulted in planning agents that were more robust and performant in aggregate. We believe that these promising results really motivate the use of curriculum learning in ML-based planning for autonomous driving in order to improve overall performance in a data efficient way. So thank you all for listening, and thank you to my co-authors. 1 second, I will be in the poster session later today if you have any questions, and I'm open to your questions.
All right, while you're thinking of questions, I'll get us started. So all robot or autonomous tasks are closed loop to some degree. So what was difficult becomes easier over time. So how does this evolve over time as difficult tasks become easier?
Yeah, so I mean, that's interesting. This is what we tried to get at heuristically with the geometric variant by starting with the more easy task and then getting to upsampling the more challenging ones. We also experimented with some adaptive curriculum learning methods that basically tuned how much from each bucket you sample based on the online training performance. And we found that that does a very similar thing by starting with like equal weights and then really significantly upsampling the hardest bucket. So it was actually quite cool to see that like these difficulty buckets ended up correlating like perfectly with the policy loss during training.
Okay, question from the audience. Drew?
Yep. Thanks for the great talk. I was wondering if you could talk a little bit more about how the crowdsourced kind of supervised difficulty metric performs with against something that's more Bayesian, like maybe like ensembling of a few different models. How good is the difficulty model, and how does this analysis change if you had a different way of representing difficulty or uncertainty?
Sure, yeah. Well, so I guess we didn't experiment necessarily with an ensemble of difficulty models, but what we did compare it to is like some maybe more interpretable heuristics like RSS and like TTE, like time to encroachment. We found that there actually isn't a very good correlation between some of these more interpretable metrics and our difficulty score. They only really work in certain scenarios, but don't generalize very well. And particularly for the hardest buckets, according to our difficulty model, the distribution of these heuristics wasn't very different from just like the unbiased distribution. So it wasn't really getting a good sense of what really is difficult and not. And so could you repeat your second question real quick? Okay, all right.
Awesome. So just a reminder, there'll be more opportunities to answer questions at the post for the first 4 out of the 5 speakers today. Let's thank Ellie again. All right, and for the rest of the session, I'm going to hand you over to my co-chair, Niels. Take it away.
Yeah, hi. So our next paper will be on topological semantic graph memory for image goal navigation. And our speaker is Nuri Kim. Okay.
Oh.
Would you have to like? I want to change the framework. There's a mirror one. It is changing because of my. Oh, I already checked it. Oh, okay, thank you. Yeah.
Yes.
Hi, I'm Nuri Kim from Urban Learning Laboratory in Seoul National University. Today, I'm gonna talk about topological semantic graph memory for image navigation. Assume a robot is placed in an unknown environment without any map information. In our image navigation setup, agent observation and goal image are from a panoramic camera. And the objective is to take low-level actions to reach the goal. To succeed, the agent must press a stop button when it reaches the goal. A graph memory is made up of vertices and edges in the form of a graph. A vertex is an area in the environment, while an edge is a connection between two vertices, representing reachability and closeness. While an edge, the proposed method adds semantic information to the graph memory by integrating object information. Imagine you are given a goal to find the cooking pot. When you know that a cooking pot is usually placed in the kitchen, you can easily navigate to the kitchen to find the cooking pot. Like this, humans use semantic context to navigate. In this work, you propose a navigation model which can run semantic context. We propose two motivations for why landmark knowledges are useful for navigation tasks. First, neighboring objects help to define an object uniquely. For example, suppose a cup in the restroom and the cup in the kitchen have similar appearances. When you look at the neighboring objects, such as a toothbrush or a snack box, you can tell that the two cups are different in usage. Second, a semantic context can be built by connecting objects to their location. A refrigerator, oven, and dining table are likely to be found in the kitchen. The topological semantic graph memory, called TSGM, is the first method that merges the image and object graphs into a single linked graph. It is made up of 3 modules: a graph builder, a cross-graph mixer, and a memory decoder. I will go over the networks in depth, starting with the graph builder. Consider a mobile robot located in an unknown environment. Our agent is tasked with reaching a goal based on a target image. To achieve the goal, the agent explores the environment. While navigating the environment, the agent constructs a memory graph based on the input. Note that the node positions are only for illustrations and not given as input. Let's discuss the basic concept of building an image graph. We extract the similarity between two locations by training an image encoder. The image graph can be obtained using the trained image encoder. Now I will demonstrate how to construct an object graph. To evaluate the similarity of objects, we employed supervised contrast learning. Since we want to create a single object node for an object, the object encoder runs whether the objects are the same even when the object is captured from various points of view. We show the top 5 objects in the environment among around 7,000 candidates. You can see that the object encoder finds query objects from the various viewpoints. Using the object encoder, we construct an object graph. The detected objects are inserted into the object memory and then connected to the current image node. When a new image node is found, the detected objects in the image are checked to update the graph. When the object similarity score is high and the categories are the same as the memory, it is determined that the object already exists in the memory. If the object exists in the memory and the detection score is higher than the memory node, the object is captured from a better view. Therefore, the object node in the memory is updated. and connected to the current image node. If the detected object does not exist in the memory, it is added as a new node and connected to the current image node. The object graph is completed by connecting nearby object nodes. Object nodes connected to the same image nodes are placed nearby. Expanding the range one step, the objects connected to the adjacent image nodes are also connected. As I mentioned, objects can be more uniquely defined using neighboring objects. Graph convolution is used to address this issue. Object nodes are self-updated with the connected object nodes. It is then cross-updated by exchanging nodes. It knows the relationship between places and objects. In the cross-update module, the image node is updated through the connected object nodes, and the object node is updated using the connected image nodes. It is performed for L iterations. The current input and goal image are utilized as queries, and the semantic memory is obtained using the attention mechanism. The action flow is composed of GRU layers produces an action using the extracted memory as input. The network was optimized using PPU. Here we illustrate an example trajectory created with topological semantic graph memory. As you can see, the TSGEM detects the target while constructing the graph memory. Our method has also been tested in the real world. The experiment was carried out on a Jaka robot. We could verify that our TSGEM algorithm was running well in the real world. In the image core navigation setup, TSGEM outperforms the baselines. It also surpasses the other topological model baselines that do not use the semantic landmark information. The result shows that our model captures the semantic context better than the baselines and can identify a more efficient trajectory. The SPL shows that. According to the ablation research on the cross-graph mixer, cross-mixing in both directions is the most effective way to incorporate semantic context. We also tested our method on object core navigation task. This task does not receive an image as a goal, but the category of an object to find, such as a chair. TSGEM shows the state-of-the-art performance compared to the baselines. In summary, the proposed method made robots understand the relationship between objects and places. A robot can find efficient paths if it knows the coffee machine tends to be in the kitchen, not in the bedroom. And second, TSGEM is the first to integrate the object graph into the topological graph, which makes the state-of-the-art result. Our work also has some limitations. Since it does not use any pose sensor and metric maps, a robot sometimes bumps into the corner. And the image nodes do not exactly represent the places, such as a kitchen, but it's just an image picture. So we have addressed these issues on the extended work we've done. Maybe check it out later. For more details, please visit our project webpage. And the poster will be presented in this room. And please navigate to our poster room with this core image. And I'm hoping to meet you there. Thank you for listening. My name is Nuri. And I'm happy to answer your questions.
Okay, yeah. Thanks for the very interesting talk. Do we have questions in the audience?
Thanks for your talk. I guess eventually you're probably going to have corruption events in the map where objects and images are perhaps incorrectly associated. Would you incrementally correct that part of the map, or would you regenerate the whole map from scratch every now and then?
Every episode, the topological graph is or made, and it is not reused. Like, is this your question, right? Or
If you're doing this in the long term, would you every now and then regenerate the whole mapping from scratch, or would you incrementally update the map?
or you have to the map is incrementally updated and generated while in one episode, but it is not reused on the other episode, like another house, like, yeah.
Right, yes. Do we have time for one more question? Anyone? Otherwise, let's thank the speaker again. Okay, is someone present for the last presentation? It's going to be online. Okay. So the next paper is finally concluding the session with some less nice obstacle behavior. So we are now looking at robust trajectory prediction against adversarial attacks. And our speaker will be Yulong Cao. Okay.
Okay, can you guys hear me? Yeah, so my name is Yulong. Unfortunately, due to some visa issues of the team, we will have to present our paper remotely. So today I will present our collaborative work, robust trajectory prediction against adversarial attacks. This work was done during my internship at NVIDIA. So trajectory prediction on autonomous vehicles is an essential task for safe autonomous driving. Because it's essentially trying to predicting the future positions of different road agents. And based on that, the autonomous vehicles can make safe driving decisions accordingly. However, like recently, there has been several attacks appearing that trying to compromise the trajectory predictions, while the attacker essentially leverage an adversarial agent driving on the road along adversarial history trajectories, and such that the autonomous vehicles will predict the future trajectory of such road agents incorrectly, and eventually will cause a collision or other severe consequences. A quick demonstration is like this. So in the benign case, well, the autonomous vehicles can driving accordingly and predicting the road agents' future trajectories correctly. And then you can correspondingly planning out the safe driving decisions to slowing down to avoid a collision. However, with an adversarial agent, which will driving along an adversarial trajectories calculated by these adversaries, you will actually force the trajectory prediction models to make the incorrect prediction, such that the autonomous vehicles will not slowing down and making the wrong planning output. And as a result, you will lead into a collision. So with that, next question we're thinking about is that how can we build robust trajectory prediction models for autonomous vehicles such that we can defend against such attacks? One common strategy for defending against these adversarial examples back in the image classification category is through this method of adversarial training, where essentially you are trying to solving these min-max problem. Well, in the inner maximization optimization, you are essentially generating adversarial examples, and in the outer minimization problem, you are essentially trying to train the model against such challenging adversarial examples. And as an end result, you can attain these really nice models that are robust to adversarial perturbations around the data points in your data set. However, we find that trying to apply adversarial training on trajectory prediction is actually challenging due to several key challenges. The first thing is that most of the trajectory prediction models are actually leveraging this generative model or conditionally generative model, well, there's a sampling process trying to predict a multimodal future. And this sampling process is essentially introducing this stochasticity, which will obfuscate the process of generating effective adversarial examples in the inner maximization optimization process, which will lead to the failure of the adversarial training. And secondly, is that we found that conducting adversarial training on conditional generative models is actually quite unstable. Compared to previous works working on discriminative models, here in the trajectory prediction task, we are mostly working on these conditional generative models. And we found that adversarial training is less stable. To validate our hypothesis, we did a simple experiments using the MNIST dataset and train a simple CVAE model, which will try to reconstruct the entire image based on a quotient of that image as a condition. And as you can see here, as the noises, which is the adversarial noises increases, the generated images tend to collapse into a simple VAE, which means it doesn't rely on the conditions. So it's just like randomly generating different images, which also explain why this is unstable and why we observe that conducting naive adversarial training on the trajectory prediction models will actually lead to some improvements of the robustness, but a lot of a huge degradation on clean performance, since it's essentially just randomly predicting the outputs without considering the history trajectories. And lastly, but also importantly, is that trajectory prediction is an important task, as we mentioned, for the autonomous vehicles. Therefore, it actually requires a strict clean performance for this task. However, we've known that adversarial training is notorious for have a huge clean performance degradation. Therefore, in order to resolve those challenges, we propose robust trajectory, which is a framework and adversarial training framework on the trajectory prediction models. First, in order to reduce such stochasticity that results in ineffective adversarial examples, we propose to use this deterministic sampling such that we have demonstrated that it can actually generate more effective adversarial examples compared to other attack methods. And secondly, we propose using a hybrid learning objectives where we not only training the model based on adversarial examples generated, but also on clean data and with some regularization such that we can anchor the learned data distribution on a fixed data distribution. And lastly, we propose to use domain-specific augmentation to further boosting up both the robustness and the clean performance. And as a result, when we deploy the trajectory prediction models trained with the robust trajectory framework, even under the attack, the autonomous vehicle can still make correct prediction results. And therefore, it can actually avoid the collision. And there's another very interesting scenario we found. Well, the adversarial agent is essentially not trying to mislead the prediction of itself future trajectory, but the other agent's future trajectory, and leads into an collision of the AV with the other agent. And we found that with the robust trajectory framework, the robust trained model can also avoid that. So in this work, we still have some limitations. First, in the adversarial attacks we considered, we are only considering these L infinity bounded adversarial attacks. And secondly, even though conditional generative model is the popular class of models used for trajectory prediction, but there's also other like frameworks like flow-based and models based on LSTM. And also, we didn't actually considering these conflating errors from perception. We assume that the attacker can just like driving along adversarial trajectories, and that will be directly the input of the trajectory prediction models. And with that, I will conclude my today's presentation. In this work, we identify unique challenges of adversarial training for trajectory prediction models. And in order to resolve that, we propose an adversarial training framework, robust stretch with key innovations, 3 major key innovations. And lastly, we conducted evaluations to show that our method generally apply to different models with the conditional generative models, and also it's effective. And for more details, please visit our website, and I'm ready to take questions.
We were told to sit in the front row and ask lots of questions. Can you hear me, Yulong?
Yeah, I can hear you.
So obviously driving behavior is very contextual to the country, even the particular city within the country. Is your aim here to develop an approach where the concept of what is adversarial generalizes across, for example, all of the cities in the US, or would you be learning spatially and city-specific models of what is considered adversarial in that context?
Yeah, so here, when we are talking about adversarial, it's essentially an specific trajectories that can fool the trajectory prediction models, and then it can lead to collisions or failure of the autonomous driving systems. So it doesn't actually necessarily meaning that we will actually have to deploy an attacker. If you think about like driving in an open world scenario, like many different kind of things can happen, right? So maybe some other car can actually happens to drive along such adversarial trajectories, which means it's a challenging scenario or adversarial scenario, which doesn't necessarily lead by an adversary. So we think by using these adversarial attacks, it can actually being used for like stress testing our autonomous driving system, such that it can potentially in the future when we deploy in the real world, it can be more robust. And the goal of this project is actually trying to propose a method to train the trajectory prediction models in a more robust way against those adversarial trajectories or unseen scenarios.
Okay, we have another question over here.
Hi, Yulong. Great talk. I have 2 questions. I'll start with the first one. Can you comment a little bit about how robustness to adversarial attacks is different from just being conservative? So in a lot of the examples that you showed, if I was the AV, I could just wait for the scenario to pass. Is there a way to maybe like quantify it or think about it?
Yeah, I think that's a very good question. I think what you are referring to when you are saying about like waiting for them to pass, it's closely related to the planner. So in this work for the demo, since it's kind of like less meaningful when we just like demonstrating the prediction results, because prediction cannot be perfect in some sense due to the multimodality future, like nature of multimodality future. So we didn't actually like present our results like quantitative results in terms of like trajectory prediction, but we instead we use a planner and demonstrating how the autonomous vehicles will behave with such adversary in the scene. But I think, yeah, partially you're saying is correct. The planner, if the planner is super conservative, it doesn't drive like aggressively. It can avoid a lot of like collisions happen. But the things that I think it's also currently like an open challenge for autonomous vehicles, like how to driving both effectively but also safely. And for another perspective, we did have like evaluation metrics in terms of trajectory prediction, because we are training for more robust trajectory prediction models. We are using common metrics like ADE, FDE, off-road rates to evaluate the model when it's under the attack.
Thank you.
Okay, with that, we are at the end of our session. Let's thank all the speakers again with a round of applause.
So just a reminder, back here at 1:15 for Fabio's tutorial, the final oral session, afternoon tea, final poster session, and then the award session and the wrap up of the conference. So see you back here in about 45 minutes.